Welcome everyone. We will begin our webinar now. Thanks for joining us. This is a continuation of AXA's annual CubeSat Innovation Workshop in a webinar format. We're doing this in a different format this year due to COVID. This year's workshop, we have two webinars, one which we hosted last week on the issue of spectrum licensing, and this is the second of the two, which will focus on how we can collaborate in Australia's CubeSat developers ecosystem. Before I move on, I'd like to give a plug to Artemis ACOT webinar that we will be hosting next month. It will discuss how will Australia be affected by the Artemis ACOTs, as Australia is both a Moon Agreement signatory and also committed to its own Moon to Mars program. So this will happen in July 9, 2020. It's a Thursday at 2 p.m. You can find the link that I will post in the Zoom chat later, or you can log into axa.unsw.edu.au. It should be on the front page. So for this webinar, we have attached some reading materials. You should be able to find that in the email that it's in the invite. In particular, in this webinar, we will cover some surveys of CubeSat standards, a survey of Australia satellite developers with some preliminary results. Some of Australian test facilities that are available. We'll talk about KUBOS, which is an open source satellite mission software. We'll discuss some common hardware problems and common issues and solutions that you can that you may face as a CubeSat developer and how we tackle them, and also RF problems and solutions, and how Sabre and Quava has a potential solution right now. We'll also discuss on how to build a CubeSat community in the Australian context. We will try to interact with you, our audiences, via Slido. So if you are on your computer right now, just go on to Slido, sli.do, in the hashtag enter AXA2, ACSER2. And you will be able to access on the left the Q&A panel where you can post questions. And on the right, you should have a questionnaire that we really encourage you to fill up as the webinar is going on. And we'll review the results of that together later. We really want to know, what our audiences are facing, what problems are you facing, and what would you like us to do a bit more. You can interact with us also in the Zoom chat, but really questions should be in the Q&A of the Slido. So Cheryl, would you like to add some housekeeping things that I might have left out?
I don't have much else to add. So I've just posted the Q&A link in the chat, and I've also posted the poll link in the chat, and they're direct links. Yes. I think you covered most of it today, Jude. So yeah, we might just pull any of the speakers' videos if we're losing bandwidth, but everyone seems to be pretty good today. So yeah.
Okay. So how many attendees do we have so far? Attendees so
Up to about 60.
60. So we have 60 attendees, quite healthy.
61. Yeah. Not
great. Okay. So without further ado, I'll ask our panelists to do a self-introduction. Before that, let me just take off my screen share. Stop share. There we go. Okay, so we'll begin with Andrew Barton. Andrew, can you do an introduction of yourself? Thank you.
Yes, sure. Thanks, June, and hi, everyone. It's great to be with you today. I am the head of engineering at Southern Launch. Southern Launch is, if you don't know it, an Australian company developing launch facilities for orbital and suborbital rocket flight in South Australia. I also have a background in the satellite industry through my time at Fleet Space, and also previously at the European Space Agency, where I was a technical specialist for a number of years before coming back to Australia, originally from Sydney, and was at Sydney Uni for a bachelor's and PhD.
Okay, thank you, Andrew. Next, Sean, can you introduce yourself? Sean, you're muted. Yep, there
Yep.
you go.
Hi, everybody. Yep, I'm Sean Tuttle. Thank you also for inviting me to participate or contribute to this webinar, my first ever webinar. Yeah, so I work for Nova Systems. I'm the space capability lead, which means I'm looking at how the company can get involved in aspects of the space industry. Before that, I spent 5 years at UNSW in Canberra, developing the space education and starting up the research there. And for 20 years before that, I worked in the European space industry, mainly in deep space missions like Rosetta and all the Mars and Venus and other missions, but also in quite a wide variety of roles, focusing a lot on testing, but also for a couple of years as a launch vehicle manager for the UK side of the company. Before that, I worked in Japan briefly and in Queensland, where I did my PhD in the hypersonics group at University of Queensland.
Thanks, Sean. Next, Marshall.
Hey everyone, I'm Marshall. I'm the CEO of KUBOS, and I'm a software engineer by trade. I've been writing code for about 25 years, and yeah, love open source, love code. I've been doing space for about 8 years now. I was fortunate enough to join a small startup called NanoSatisfy and work on 3 CubeSats that were sent to the ISS. That company decided their business model wasn't any good and rebranded as Spire. So I got to be the first software engineer there, and that was a pretty crazy experience. Took that experience and my open source background to start this company. I'm pretty much a nerd. I just really like writing code, and I really like space. So those are both nerd things that line up with being a nerd. Yeah, I've done a lot of open source stuff in my past. I've worked at Red Hat and JBoss, worked at Accelerator and Mozilla on the Firefox OS operating system. My background is in embedded software and web software. And that's what we do at KUBOS. We focus on the flight software and the operation software for your mission. We'll talk about that in a little bit. And thank you for having me.
Thanks, Marshall, all the way from the US. Andreas, give it a go.
Hey everyone, I'm Andreas Toniadis. I'm the director for Sabresh Nordics Australia. I'll be talking a lot about standards and things today, so looking forward to diving into that. Some of you may know me from my old shindig, Obelisk Systems, working on developing CubeSat hardware, prior to that, I've worked in many different deep ground engineering roles. I've worked with several space startups of late. And I'm a PI for Guava, which is a collaboration of university bodies and industry for a training center with CubeSats. Thanks.
Thanks, Andreas. And Xue Liang.
Hi everyone, I'm Xue Liang Bai. I'm working as the training center engineer in the ARC training center for CubeSat UAV and their applications, namely Guava. Before this, my master and PhD is in the uni. I went to Singapore, joined the Center for Quantum Technology, and built a 3U CubeSat and sent that to space a few years ago. So today I'm here to share some experience as a satellite builder and the difficulties, the challenges that we met, and some suggestions that I have to build a local community. Thanks.
Thanks, Xue Liang. So for those who just joined us, go ahead to Slido and you can put in some questions there, and please fill up our poll. We'd like to know more about you. So we'll go ahead with our first presentation today, Andrew Barton. Please start sharing the screen and we'll go from there.
Okay, and unmute. Are you seeing the full screen presentation?
It's a preview version.
or of a preview. Okay, I got it wrong. My apologies. Stop share, reshare. It's very hard to tell which one it is. Okay, there we go. Right, how's that?
Looking good.
Okay, so I'm here today on behalf of actually two different organizations. One is Southern Launch that I mentioned in the intro, but also on behalf of the SmartSat CRC Aurora cluster. And the topic of my presentation here is SmallSat standardization in Australia. And in fact, with the Aurora cluster, I'm helping to investigate this as part of a special interest group. So the Aurora is a separate company formed underneath the SmartSat CRC, which gives a chance for the startup community in the space sector to get involved in CRC activities. And there's a web link there that you can go and learn more about it. The Aurora cluster is just forming now, so this website will be updated as time goes by. It's a relatively new project that I've been working on. And essentially what I've started with is this question. What are the opportunities and needs that exist within the Australian space sector for standardization of small satellite missions? And I would just emphasize opportunities and needs. So we really want to be user-driven here. And also small satellites. So obviously our country doesn't have a history of building large expensive satellites, but we have a great opportunity to innovate at the smaller end of the spectrum, which is also where the global satellite industry is going. So this is where we think there's the greatest opportunity to do something in the area of standardization. I would just point out that standardization can be defined as a rather narrow thing, which is technical standards, and we would have all read and used technical standards throughout our careers. But there's also, I think, a sort of more useful, broader definition, which would include other things, identifying and communicating de facto standards, things which are not yet sort of formalized by some authoritative standard body. And in general, anything that can support those things I've listed there: compatibility, interoperability, safety, repeatability, quality, or commoditization, or formally custom processes. So I think that fits very well within the theme of this panel today as well. Now, when I was working at ESO, I had the chance to work on a few standardization activities. And so I just want to sort of highlight to you all that within the ECSS system, so the European Cooperation on the Standardization of Space, they explicitly break up the different types of standardization activities I just mentioned. And so the top category, which is the standards, which we are all familiar with, is there, and they definitely exist, and they're definitely used within the European space scene. But perhaps equally important, or in some people's eyes more important, are handbooks. And I certainly saw firsthand the desire of the space industry to have handbook type information where they can get advice, guidelines, and tips on how they can develop their systems in a way that's both, quality and reliable, but also interoperable with the rest of the community. Of course, the Spickle Space Project has got many companies that have to work together. And there's also another category called technical memoranda, which is sort of a bit more ad hoc information, which is useful nevertheless, but not really in the form of normative standards or handbook material. So if we were to do something here in Australia, we could be inspired by this model. If you've looked at NASA or other standards, you'll see that they do have some similar concepts, but I think, as far as I know, ECSS is the one that divides it up most cleanly here. So what are we trying to do within this Aurora cluster in terms of SmallSat standardization? The vision is that we want to have open participation and domestic and international. Of course, we're going to be led by what are the needs here in Australia, but not not blind to what's happening in the rest of the world. It needs to be voluntary compliance, at least in the early days, because we don't want to stifle industry or innovation. It's bottom-up, not top-down, developer-led. And another important aspect is that we want to maximize the benefit that the SmartSat CRC parent body and the ASA can bring to bear. And so we'll be looking at ways that we can be mutually reinforcing with their activities and plans. And a final point I would just add is some standardization efforts can go awry when multiple supplier and multiple user scenarios are not rigorously pursued. And so I think that's an important thing to look for. It's not really going to be a particularly useful standard unless you have both of those things. So what I've been doing is interviewing, to start this project off, interviewing the small satellite developer community in Australia, and just collecting and synthesizing their views on the standardization problem. So I've listed here the organizations who I've interviewed so far. There are more which I intend to interview, and indeed on this webinar there may be some people who feel like they could contribute to this early stage of investigation. So please do contact us and let us know. We'll be happy to have a one-on-one chat about that. And through those interviews, I've categorized a number of common themes where different parties have expressed an interest or a need, and I've ranked them according to how many different interested parties there were. And so we can just run through those ones quickly. So in the first category is the launch vehicle interface and satellite structures in general. So in a sense, this is looking at what do you do once you go above the existing CubeSat standard, which is by nature a mechanical interface standard. What do you do for larger satellites? Does just scaling up that cube format work, or do you really need to look to other methods for connecting to your launch vehicle and designing your structure? That was quite popular. Now Southern Launch, of course, we're in the launch business, so we'd love to have lots of satellites in Australia being built in this weight range, which is where the small launches that we'll be supporting will be operating. And the same would go for the other launch companies in Australia who I do intend to include in this, but haven't yet had a chance to speak with. The next one is avionics, internal electrical connectors and communications bus. Pretty much goes without saying, if you've ever worked on a CubeSat project, you'll see that this is a bit of a mess, and it's very difficult to innovate when you're struggling with making the component from one supplier talk to another supplier and still fit within the same sort of relatively limited volume. Another one that came up is telemetry downlink. I didn't expect this, but it was quite interesting how many people saw this as a problem. It's obviously a big headache in the CubeSat developer community, so having ways to standardize that is advantageous and perhaps closely linked to the SmartSat CRC theme for advanced telecommunications. And payload data communications, in particular being secure and bus independent. This is somewhat related to this one, maybe even could be joined into one theme, but really focusing on if you're flying a payload on somebody else's bus, how do you get that sort of control over your payload and not have the bus getting in the way of that or getting to snoop into your data. Another big one was of interest for a few parties at least is mission assurance and system testing. So this is how do you make sure when the satellite is launched that it has a high chance of success upon reaching orbit. The CubeSat sector has a pretty miserable record of that kind of thing, and so bringing it to a more professional level through some sort of standardized approach of the testing you have to do could be very valuable. And just very briefly touching the other one, so we've got the software operating system. KUBOS is on the line here today. Hi, Marshall. So maybe there's some more topic, that topic can be discussed some more later in this panel. radio spectrum licensing, concurrent design systems, and payload data format. All of them came up at least once. But so this is not a definitive list. Just wanted to sort of throw it out there where we are now. It's a snapshot. Interested to hear from others, people, what they might like to see in terms of standardization. And I would just point out that the Aurora cluster is likely to support a small number of these as sort of standardization committees, not all of them most likely. So we'll be looking through, well, first we'll be finishing this survey that I've started here, and then we'll be identifying the areas of maximum impact and also most relevance to SmartSat CRC's activities. And I should also add their ASA activities. Then we will form some committees, and probably to start with one or two. We'd really like to get the ball rolling with some the maximum momentum, let's say, and to make the maximum impact. And along the way, also seeking international inputs and partnerships and communicating the vision to the Australian community. So that's all I actually have to present here. As I said before, you'll be able to follow our progress through this website. There's nothing there yet on this particular topic. And if you'd like to speak to me about this survey, you can contact AXA and they can provide my contact details. Thank you.
All right, thanks, Andrew Martin. So next, can I invite Sean Tuttle to share your screen? And
Right.
right,
Can
Sean, we
you
can see it clearly.
can you see the slideshow version, or again?
Yep, that's the
preview?
correct slides. That's the full screen.
Cool.
So take it away, Sean.
Okay. Yes. Well, thanks again for having me. I'd just like to say, well, what I'm going to talk about is a little bit about testing, because as some of you may be aware, and I guess that's why I was asked, here's I've been doing a couple of audits and surveys of testing capability across the sector in the country for the Australian Space Agency and also for the Northern Territory government. So I can't give much detail on the results of those because they're still underway and the agency needs to release those when it's ready. But I can give you my own perspectives and what I found and some general thoughts that hopefully might be interesting and helpful. And secondly, I just thought I'd touch on a few philosophical things while I was here. So I thought while I'm cultivating this new role for myself as being an annoying person that crops up and you wished you hadn't invited because he keeps raising awkward issues, I thought that sounds like a good role for me. So the first thing I thought I would do is take issue with the title of today's webinar. But before I do that, I should say it's very timely and it's a very good thing that AXA is doing. So I applaud them for that. But I just wanted to say, well, CubeSats made easy. Why should they be made easy? And why should we be looking at streamlining? So basically, in my view, it's important to recognize when things are difficult because for many reasons, we gloss over things a lot. There's a great tendency we have to use sayings like, oh, too easy, mate. And miss complexity and difficulty. And there's value in those things. And there's value in treating them accordingly. So we learn a lot more from things if we credit them with the full degree of difficulty that they have. So related to that, historically CubeSat started out life as educational devices. So again, let's remember that and make sure that we get the most out of the experience. So while we want to streamline things, there needs to be a valid reason for that. So what I'm saying is there's a lot you can learn by learning by doing is the best way in my view, and that's what you can do using CubeSats. space is hard. It's still the same place it always was, even if you use labels like space 2.0 and so on. So the path you take to getting there determines how well you end up functioning there. So whether you do things in a slapdash fashion or whether you take care. And if you take care, that's more likely to occur when you've acknowledged that it's quite a difficult thing that you're doing, and you think about it deeply, and then you're more likely to succeed. So I think we should be thinking about CubeSats being made reliable more than being made easy. When it comes to streamlining, yes, it's always a good thing to see what's been done before and what you can learn from. So the old classic of avoiding reinventing the wheel. But this goes back to, again, what is the purpose of what you're doing? If it's to learn in the traditional CubeSat sense, then by avoiding some of those steps and not reinventing the wheel, you're not acquiring that knowledge deeply for yourself. So be aware of that and decide why are you doing this? Is education and learning a critical part of the undertaking? And then if so, it's no crime to reinvent the wheel, because you'll be better off for it usually afterwards. On the other hand, if the CubeSat is just a vehicle for getting into orbit and delivering something else, so it's not the end objective in itself, then yes, you want to learn lessons wherever you can and streamline the process and not waste time reinventing the wheel. So those are just a couple of philosophical things I wanted to start the day with. Similarly, about testing. So why do we test? We should always be asking ourselves these questions. And there are fundamental differences between the types of tests that you do and the reasons that you're doing them. So for example, we need to be aware of things like who we are, why are we doing this? Are you a university and just trying to learn something, or are you a commercial enterprise? In which case you're going to consider the tests quite differently. And on this slide, I've ranked them in kind of 3 levels of complexity, criticality, and reasons or benefits to you. So number 1 is doing the testing for the launch provider. So by using CubeSats, when you meet the requirements of the CubeSat design specification and do your thermal bakeout and your vibration and so on, the main thing that you're doing, and probably most of you are aware of this, but still a surprisingly large number of people are not aware of this, all you're doing is making sure you don't damage the launcher, their main customer, or their reputation. No, they do not care if your CubeSat works. It just needs to survive in a single piece, basically. And this is what you get with that level of testing. It says nothing about will your CubeSat work in orbit. It just tells you that it'll survive the journey there. The second, and this is what I was going to say again about following the CubeSat standard and using this whole approach, you're spared some of the complexity and hassle of designing that you typically encounter with a big satellite, where you need to worry about, are you going to fit inside the launcher fairing? Because no, your volume is already predefined and you fit inside your dispenser. Okay. Are your radio emissions compatible with the launcher? Well, it doesn't matter because you're not under any power, and so on. So a lot of the complexity is shielded from you as a developer when you're taking the CubeSat approach. The second level of testing would be tests that you do for yourself. So now you want to see if your system works. So now you might start assessing the RF link, start playing with making sure the software works. You might even be doing that under thermally representative systems. And now you're looking at, does your CubeSat, is it going to work in orbit? And then thirdly, you just do more and more of those sorts of tests. You might want to expose some components to radiation to see about their survivability. You might look at some of the self-compatibility electromagnetically, do more complicated functional testing of the software under thermally representative conditions and so on. And when you've got to that level of testing, that's showing you yourself that your device is going to work, and also giving confidence to the other people out there who you're hoping to charge for your services and so on. So this is just a very general overview of testing, and again comes down to who you are and what you're trying to achieve. So that's just to set some background for testing. Standards, from what we found from the survey, standards are not widely used for space technology testing in Australia. The fact that you're following the CubeSat design specification doesn't mean you're following any standards, even though the tests, that's a specification, a design specification, not a standard. The tests implicit in that, if the launch vehicle company is fairly on the ball, then those tests will have had some either ECSS or GEVS type standards applied to the levels, and so on. So just to be aware of that philosophical difference between a specification and a standard. And standards apply to many things. So I think today we're talking a bit, possibly largely focused on testing, but as you saw from Andrew's talk, those standards can apply right across the spectrum from how you design the processes, like systems engineering, etc., management processes, manufacturing. In the ECSS world, it specifies things such as, do you need to perform a fracture analysis on your propulsion lines, and under what situations. It specifies what color insulation to use on your electrical wires, and all these sorts of things. So time is ripe for us to start considering the adoption of some of these things and tailored in a way that makes sense for us. And definitely there's the possible issue of stifling, but more importantly, there are the issues of making us more competitive globally, making us able to plug our products into foreign systems, and just generally improve the quality and the way we do things. So it will be a good balancing act, but it's a good time to be considering those things. So again, that's why I say this is a great time for AXA to be holding these sorts of workshops. Just going to the survey on the test facilities. These are some of my observations and opinions again. We have a lot of stuff already. We need to consolidate it and how we use it. From my predictions of how the sector is growing and what we've got, we can absorb significant growth in the demand, like in the annual number of units we need to test each year, simply with what we've already got. However, there are gaps here and there in specific features about some of the things that need to be addressed. One of the ideas I've had, and you'll see from the next slide probably why this thought springs to mind, and that is, it may be a good idea to ensure that we have some of the basic core testing available in all the major centres around the country. And when I say the basic core testing, I'm talking about point number 1 on a couple of slides back, for the tests that satisfy the launch service providers. So not all the more exotic or interesting ones, but just simply the ones to be compliant with your launch vehicle provider and get on board. Simultaneously, I think we need to ensure the survival of the AITC, because it's a unique national capability in many ways. But we're still a small market, and the numbers that we're seeing in numbers of units that need testing is still not that high, even if they grow healthily over the coming years to sustain these things. So we have to be careful with what we do in the next year or so in terms of investing in more facilities. So we want to avoid creating white elephants, in my view. And there's the old issue that many have with this obsession with shiny new things. So I think, again, it's quite a good time to be removing some of the focus from the testing hardware, the facility test equipment, and focus on some of these intangibles like we're doing today, standards, how are we going to apply them, if we're going to apply them, and making sure there's some continuous expert advice available for newcomers. Yes, okay, so here is a map we've compiled based on looking around the country at test facilities. And what you'll see is that in most cities there's some form of vibration testing equipment. There's often some form of shock testing. There's more often than not some facility for thermally cycling under ambient pressure conditions or even low pressure. Thermal vacuum is a bit less common, but we know from numbers out there that that are listed that there is a growing number. There is the ability to do EMC and RF testing in all centres, really. And there are the foundations, shall we say, for doing radiation testing in a couple of locations. And as with all things, the devil is really in the detail here. So while I say, yes, maybe you can go to Melbourne and find 5 EMC chambers, this is not saying that A, they have the right equipment, measurement equipment for the chamber, B, they may not be clean enough for space work, C, they may not cover the right frequency range and so on. So this is a kind of high-level snapshot, and what it's saying is, or what I'm saying is, we should maybe address consolidating all this and going into those details and adding and fixing them so that there are a decent number of space-capable facilities all around it. And these ones here that you see are housed across commercial test houses, universities, defence establishments, and private companies. So I'm not specifying where they are either. I'm just saying that there is some kind of capability there to be worked with. And quite a few times in this survey, people said, "Oh, what we really need is a thermal vacuum chamber, or we need an EMC chamber." And it turned out that that person wasn't aware that within 5 kilometers there was one sitting there waiting to be used for a fee. But what we need to do is make this all clearer, consolidate it, and then start using it better and more. I've added this in because I found this quite interesting, and this comes from some of you as well. One of the questions in the survey was about what you view as the main cause of failure in space systems. And of course, we know all the traditional ones, but I think it's important to see that far and away, the majority of people recognized that just insufficient testing in general was probably a major cause of failure. And in particular, no integrated system testing. So that's the level 2 and the 3 in that slide a few slides back. And the others, also a couple of company organizations recognized a lack of general access to skills and some clear standards and guidelines. Finally, these are just some almost random observations, but are relevant to today's discussion. I don't know if most is the correct statement, but I think quite a few of maybe the more established Australian space startups are buying their CubeSats from overseas because they come with the comfort of flight heritage and having been tested to recognize standards. So again, this goes along to where the reason for what you're doing matters. If you're not doing this for purposes of education, but you're you want to get to orbit to deliver a service, then you're going to look around for cheap, reliable platforms that are tested to standards. So how this plays out for local companies trying to develop CubeSats or SmallSat platforms will be interesting, and how this in turn influences the demand for testing services is also something that we need to watch. Yes, and there's definite growth in a number of universities in the country and R&D organizations in general that are planning and have funded CubeSat missions. So this feeds into the testing demand as well. And as I said, commercial organizations make their choices differently about the platforms they buy. And so I think the last point on that was just, it's a question over our overall sustainability of the testing infrastructure we have in the country that needs to be kept in mind. All right, thank you.
Thanks, Sean. So for those who just logged in, please join us at Slido as hashtag AXA2 to fill up the polls and to add more questions in there, or to even upvote some questions there that are relevant to you. So next, I'd like to introduce Marshall. Marshall, you're next. You can start sharing your screen.
Sure thing.
And make it full screen. Yep, we're good to go. Thanks, Marshall.
Yeah, my pleasure. Thank you all again. Yeah, so there's a lot to talk about with standardization. As Andrew sort of rightly pointed out, standards are not just about what a standards body decides in a room. They're also about what is sort of emergent in a larger community. And sometimes standards are de facto, even though they haven't been decided on by a committee. And we see that a lot in early markets and early technology. And we see that a lot in the open source community as well. And my specific background in open source is kind of where I'm coming from here. And so I've actually worked on both standards bodies and major commercial open source projects. And my introduction to the satellite world was a really interesting one. So let's just kind of go through that. So hi, I think I went over this in my intro, but my name is Marshall. I'm a nerd that loves open source and writing code. You'll find me in Vim writing my code. That's pretty much what I love. But you know, anything in code related as it relates to space is what we'll go through here. So you may recount my horror when I first was introduced to the word CubeSat in 2012, and I came across a small open source project, actually the only one I could find on GitHub, that would allow you to reuse a library to send a very basic command or telemetry packet over a radio network, over a radio connection. This is the source code I was greeted with, and this was about the length of the documentation I was given to use this great library. And while I do have a lot of experience writing C code, and this wasn't completely foreign to me, if you've never dealt with systems code or C code and you looked at this, you'd probably start getting pretty freaked out. Rightfully so, because data and data standards should not be this difficult. Now, to be fair, in 2012, things have changed a lot in 8 years. When I first saw this, this was one of the only open source projects you could find. And not only that, but the state of the technology, both commercially and in the education sector for doing communications in CubeSats was way more primitive than it is now. And it was actually much more the case in 2012 and even prior to 2012 that most CubeSat radios were using VHF or UHF. One-way radios. And so they would have to bit back as much data as they could in a pure binary format across the wire. And that led to very arcane code and arcane sort of understandings of telemetry formats, command formats, packetization, and everything in between. And so luckily, I saw the problem and I decided I wanted to help. I wanted to fix the problem, come and help. So with my company KUBOS, we've done basically two things. One is to try and help standardize and make really simple the act of integrating your mission into stuff that's off the shelf. Now, as Sean also mentioned earlier, that it really does matter what you are trying to do in your mission. And if you're trying to learn everything there is to know about, the bits and bolts of from the ground up, running your mission, it's not always best to use something off the shelf. On the other hand, if that's something that's off the shelf is open source, you kind of get the best of both worlds. You get something that's reliable, that can be deployed commercially and much faster, but you can also use something that helps you, that shows you its underlying nature, and you can learn from that. So we kind of combine the best of both worlds at KUBOS, and this is what we do. MAJORTOM is our operations software. This is a web-based, cloud-based operations console that includes GraphQL APIs for commanding, includes WebSocket APIs for sending telemetry back to the cloud, has open source clients for both Python and Node.js, and supports a litany of existing both protocols and vendors. And not only do we obviously support our own flight software and some of the open standards like ECSS Space Packet, but we've gone through a lot of the commercial vendors too that have their own ground stations, testing harnesses, and ground networks, and we've added support for them as well. And we've got flight heritage already on 2 satellites, with another 2 launching in the next couple of weeks here. And so with MAJORTOM, this is sort of our cloud software. And what I wanted to talk about here was that you don't have to think about how I'm going to re-implement the wheel, reinvent this whole operations console. How am I going to track my satellite? How am I going to point my dish? How am I going to do all these things? Well, really straightforward. You go into our website, you sign up. It's free to sign up. You write about 8 lines of Python code. You connect your mission to MAJORTOM. You start giving it telemetry, and you've literally got hundreds of metrics per second throughput right off the bat using MAJORTOM without having to write a single line of code. Now, it's important to understand the performance trade-offs and all the different infrastructure that goes behind all this. But at the end of the day, if you just want to test something, this is great. But it's also great for a commercial setting where you want to not just see the telemetry, but command it as well. And so MAJORTOM has been built with this idea in mind. And so this is like step 1 to like understanding your system from the ground side, connecting to the cloud using an automated mission operations. But the other thing, and this is really where the bread and butter of where we started with this concept, was KUBOS. So if it isn't completely apparent by now, KUBOS is KUBOS, that's CubeSat operating system. I was very clever in the naming, as you can tell. And basically the idea is it's an open source Linux-based operating system for CubeSats. It runs on a litany of different vendors, too many to list actually. We've got most of the major commercial CubeSat vendors have some compatibility, and a whole list of other offshoot implementations for things like the Raspberry Pi. But we focus on a couple of things. One, we wanted to be performant. So Rust is the language that we use for systems. So that's both performant and safe. I don't know how many of you guys know about Rust, but it does things like automatic memory checking in the compiler, things that like C or C++ won't do for you. We also have our own standardized API for subsystems. This is a like real basic concept like that the mobile world got really right. Like most attitude control systems give you a quaternion. So why don't I have an API to give me a quaternion from an attitude control system, and then just a vendor implementation for each vendor? Those are the sort of like no nonsense things we did from day 1 in KUBOS and sort of enabled that in our SDK and platform. We have over 700 people in our open source community. Again, I think we're not only like one of the first of our type in the CubeSat world, but we're definitely the largest of our type. You know, so many people using KUBOS in different contexts and different missions, everything from CubeSat missions in universities to commercial missions. And then from a standards perspective, we look at KUBOS the same way we do with MAJORTOM. At the end of the day, these are service-oriented architecture systems with web-based architecture. We should be using web-based systems. And so we use GraphQL for commanding. We use JSON for telemetry. We obviously compress it. We don't use it over the wire in JSON. And then we use CCSDS, Space Packet, UDP, and a whole list of other technologies on board for getting information both between subsystems and down to the ground. We have flight heritage on 3 satellites with KUBOS today. There's a nice little diagram here on the right. Unfortunately, KUBOS is not as pretty as MAJORTOM. It's harder to demo. but you can go grab it on GitHub right now on github.com/KUBOS. And basically, you know, what I want to nail home is that, you know, we tend to think of, I think, software and really just technology in the space world in general as very sort of cut in stone and hard to learn and hard to access, and like we need to treat it like a baby and we need to treat it and make it perfect. And that's all good and well, but you know, what we should be looking at when we think about iterating and innovating is like, how do we stand on the shoulders of giants, and like how do we iterate and do so safely in a responsible manner? And with open source and the technology that we're creating at KUBOS, we're trying to show a different way where we can collaboratively work on software together that improves the state of the art for the entire industry, instead of trying to all go do it in our own silos, which has been the way this industry has been doing it for way too long now. We're trying to improve that situation. But one more thing I'd like to add, and you know, sort of a Jobsian moment here, our little one more moment thing. We're offering MAJORTOM to developers starting today for $25 a month per satellite, and that's to start enticing more and more people to get into the industry. We obviously have our enterprise and on-premise pricing and stuff for big companies, but we really want to entice especially university students. We've had a lot of success getting university programs into our products, but we want to have a really low-cost way for people to really just get their feet wet with using off-the-shelf software. And so you can just go check out our link here at kubos.com/try-MAJORTOM. And yeah, that's me in a nutshell. I love open source. I love software, and I can talk about it all day.
Right. Thanks, Marshall. It's just great to have you all the way from Texas, and it's about 11:54 p.m. over there right now, isn't it? So thank you so much. Next, I'd like to get Andreas. So yeah, we've got about 10-minute slot for you and another 10-minute slot for Shirley. So give it a go.
Alrighty, I'm just going to quickly share my screen here, and if you can let me know if it works. Can everybody see this?
Yep.
Excellent, wonderful. So today I'm actually going to be talking about CubeSat standardization, dealing from the implementation side with hardware, software, and the rest. I've already touched on who I am and what I do, but the topics I'm going to be addressing are CubeSat hardware problems that we're looking at in general, a review of CubeSat community standards, and I'll start with some RF problem solutions, but I'll let Julien take the majority of that. This is going to be an intro into what we're doing with Guava. I am conscious of time, so I'm going to try and not dawdle too much. So, starting with CubeSat hardware problems, there are a number of problems that currently face the industry from standardization of physical hardware. And the first is interconnectivity. So one thing that we've seen a lot is that one brand doesn't work with another with your CubeSat hardware. And basically it doesn't just mean relating to the CubeSat PC104 standard, which a lot of people are familiar with, but other physical standards too. So they can't even clip together despite all adhering to the same CubeSat standard. Another issue that we have is some manufacturers offer things that others don't, and as a result, you end up having to entirely invest yourself in one single ecosystem. Which leads to another problem that we've had lately. If you have to buy one spacecraft or component, you often have to buy into that entire ecosystem, else it's not going to work at all. And as an extension of that, often if you need a function for your mission, especially with COTS stuff, you're often getting one thing that you need and another thing that you don't. So that's another problem. And number three, another problem that we currently have within the industry, and it's not going to be all doom and gloom, and we'll get to the good things soon and how we can fix these, is that payloads are all relatively bespoke at the moment. That's a good thing and a bad thing. So the CubeSat bus has to be flexible enough to accommodate a large variety of payloads. And the thing is that these payloads being specific for a task often require specialized interconnectors, unconventional power requirements which won't be available from certain vendors. So for example, 12 volts, 48 volts, etc. Certain current requirements in order to function. Now, an exception to this when it comes to large amounts of CubeSats being manufactured is constellations. So if you've got, for example, Planet. Planet has hundreds, or at least 100 CubeSats in orbit. They're all the same. And as such, it's just a case of mass manufacturing. But for off-the-shelf new missions, if you have a specific payload, then you are going to have to make some compromises in order to make that work. So why don't we just standardize things, which I guess is the big discussion that we're having at the moment with regards to this problem. That has been attempted to a certain degree, but there is also a long way to go, and I'll just kind of dive into it. But essentially what we're trying to avoid when we want to work on a new standard is not to start with 14 standards that we're trying to consolidate, as this XKCD comic says, and end up with 15 all competing standards. That's what we want to avoid. So we have to be careful how we progress as an industry in the future. Some of the standards that do exist, and I'll just go through them quickly, and have been relatively successful. So you've got the original CubeSat standards, which are your interconnecting, your physical dimensions, the PC104 header. They work quite well, obviously. That's the definition of can your box fit in another box, which fits in another box and then gets launched from a rocket or the ISS. And that's basically where that ends. There's been some good success in open source and standards approaches from an initiative called LibreCube, which is worth looking up. LibreSat is another name as well that it might fall under. And they've basically got a GitHub spacecraft. And that's been a journey since probably 2015, I think, which has been quite successful. George Washington University CubeSat Framework, another one to look at. Essentially guidelines. And it's the same with NASA's CubeSat 101 guidelines. So again, they are almost like an instruction manual on how to do things, but there's no standardization of the electronics, the bus, communication standards and whatnot. Others to look at, we had Andrew already talked about ECSS and similar, so you're aware of what these involve. They are not going to give you a full interoperability between payloads, which is something that we really want to go to. And then my two favorite ones, obviously QB50 is the closest I think we have seen, where there was specific rules and guidelines which enabled a constellation of 50 CubeSats to create a large number of set experiments in orbit. In saying that, though, whilst they are the closest thing we have to standards, they were set experiments and payloads for this, which is a distinguishing factor. And if we can go basically down the road that QB50 has gone down, plus making ubiquitous standards, then we're on the right path. And then of course you've got Marshall, who just talked about KUBOS and everything, and from an open source software perspective, that's awesome. Sorry, I was gonna. Okay, so to go on, there has been little progress so far beyond these standards. And whilst we have globally adopted the CubeSat standard, only a few true hardware standards exist. Like I've already discussed in the previous slide, we have guidelines, but we don't have a fleshed out standard that involves physical, electrical, and communications that allows for that ubiquitous component interoperability, like getting those two cards that from two different manufacturers are going to slot together. Even if you adhere to the PC104 standard today and you build a satellite part, or you buy two different ones, if you plug them together, there is a good opportunity that they will explode. So that is one problem that we're facing. Back at my old shindig with Obelisk Systems, we did try and do this, and we worked on an electrical comms standard that doesn't really exist beyond an original draft, but the response was strong enough back then that I think now, given we're relatively established as an industry, we could try and do something again. And looking at what Aurora is trying to accomplish, as well as SmartSat, the time seems perfect for this. And yeah, we're close enough as companies that we can give this a go. To give an idea what it really looked like, it kind of went down into the independent pin layouts of the bus, as well as voltages, as well as communications protocols and whatnot. So it was a pretty comprehensive document, and I think building up a new standard based on these, on something like this, would be a really good step forward. So how do we fix the void that we have at the moment? Well, step one, we bring together an alliance of companies nationally who are committed to building proper standards. Step two, we create a digital resource repository that allows for the collaboration between CubeSat builders, university teams, and hobbyists. Step three, we start with a simple demo, like just a mission. We choose some arbitrary mission to set a benchmark, and we build up a standard bus design through a standard satellite mission design process all together, but documenting the standards at the same time. And then what we can do is we can test the effectiveness of these standards for a prototype project, either in a 2 or 3 U spacecraft, for example. And what that would mean is we take a number of different companies, and they all come together with what they've designed as their CubeSat board. So for example, an EPS or a onboard computer. And we see whether the standards that we've worked so hard to define can actually work. If we can integrate this thing, then it's a good step forward. If it doesn't work, then we iterate again until we find out what problems led to this incompatibility, especially between universities and companies here in Australia. And if it can fly, why not fly it, And I'll just quickly go through my part on the RF problem solution section. It's more talking about the story, and then Julien can dive into the nitty gritty. So the problem that we had was we needed solid space and ground station infrastructure, both for Quava and with Sabre as well. Sabre was looking at having a number of new components and really beefing up our back end. So as Quava was getting off the ground, we thought if we're going to do a mission with them, which we are doing, we wanted to also be client agnostic for future operations. And in addition to that, 2 of us from Sabre, Jason, Held, and I, are PIs with Quavas who have already been engaged heavily. So we thought, can we actually design an open solution to help as many future missions as possible? And of course, the solution to that, obviously, like I've already mentioned, is we're working with the Quava team directly on building the ground station, building our server infrastructure, building the commands at the server, the APIs and RF decoding stacks, and with the intention of making this available to a lot more people in the future. Another thing that we've done is we've made a really easy to use API. We've got a bunch of API endpoints that allow for pretty much anyone connected to our system to get what they need for their mission operations, for anything related to our data processing, including TLE databases, etc., ground station control. And we've been working to make sure that's all integrated into our flagship mission operation platform, Piggy, which you can get some more information about at our website, sabrerush.com. I won't go into too much more detail on that because we are a little bit tight on time. And there's just a cute little picture of what the original UC ground station looked like. And we've been experimenting with different antennas on our end and trying autonomous decoding of things, and we've been having a lot of fun with it. So what I'll do is I'll pass on to Julien now, but that's me. And Julien, if you want to take over with your presentation.
Yeah, thanks, Andres. So I think because the time limit, I don't really want to kind of go into too much details on how we build the ground station. We did have a lot of difficulties. We were really lucky that Sabre is only 15 minutes away, so we can sit very, very close to each other and just, talk what are the problems. But the difficulty we've been facing is because of this lack of resources, we had a lot of trial and error things to do. We don't really have a recommendation or a suggestion say, okay, these are the things you can use that will work straight away. That hasn't been happening yet. And I know many people been advertising, many companies been advertising, hey, we have a turnkey solution, yet they don't. So a lot of collaborative efforts need to be done closely between the ground stations and the satellite developers, and that's being a big part. It's just a lot of end-to-end tests happen too late, which resulted the failure of the final satellite. So yeah, I guess that's enough about that. So one thing I want to add on the ground station aspects is I want to show you this diagram. So a few years ago, you wouldn't find so many frequency users on the right-hand side. So most people would focus on the VHF side. But these days we are seeing more and more. We're talking about building a ground station network or a national kind of ground station database. I think we should be considering build more higher frequency bands, ground stations is higher bandwidth, because we're building more complex satellites. We're doing more complex things which will require higher bandwidth, and this eventually will become a bottleneck for satellite developers. And I totally see like a lot of missions are limited because of the limited bandwidth. Okay, so so here's really my slide. So what I really want to talk about here is from a satellite builder perspective, what are the challenges that I'm facing? So one of the major things is, I think currently we don't really have a turnkey solution, like I just mentioned. Also, a lot of manufacturers give very, very long lead time. We obviously don't have local suppliers in Australia for all of the parts and subsystems. So we often being overly optimistic and book a launch date maybe a year and a half. Then we realize the satellite suppliers take about half a year and more to deliver, and even worse, after half a year, they give us a call saying, "Oh, sorry, we can't deliver. We need to cancel your order." So that would delay a CubeSat project, which mean to be small and quick, but often not the case. The other thing will be budget and manpower issues. This is the case for most universities, okay, for startups. So we are also facing, issues that our payload providers are more and more demanding. They need like higher bonding requirements. They need more power. They need, bigger satellite basically in general. So the last thing I faced very, very recently is because of the regulation licensing issues. We have to delay our project by quite a lot. I think we covered most of it last week. If you missed that seminar, we're happy to share more offline. So yeah, so those are the complaints, but I'm not really complaining. This is, it doesn't mean like my life building a satellite is usable every day. I love my days building a satellite together, but this is the reality we're facing. That's why we need standardizations, we need community support. I'm personally very much against that we build a satellite standard from beginning, because it won't be necessary as covered by Andreas and others. But instead, we may want to go for some sort of QB50 alike. So we have a template of design review documents. We tailor and take whatever we need from the ECSS standard or JAXA standard. We do the tests that we need, and more importantly, I think if we can kind of do a peer review system within Australia, that would be good. So I had this in my previous job when I was in Singapore. We invited a lot of experienced satellite engineers, including University of New South Wales in Canberra. So they sort of give us a lot of criticize, and we really improved after the critical design review period, and that really lead to a mission success. So other things I think other people already cover, we need to share resources. But I want to go into a few like smaller things, like can we have a before flight checklist? Can we have part recommendations and building things? What are the things I can use? What are the things I can't use in space? What other local suppliers, including smaller ones like cable connectors, screw and nuts, manufacturers, PCB manufacturers, mechanical cable, etc. These smaller things, it doesn't appear to be very important, but when you actually start to build the building process, this thing will slow you down if you don't know the right person to ask. And the national database for testing equipment, I think that's already well covered by the previous panelists. The last thing is what not to do. Lesson learned. This is a particularly interesting one because if you ask a CubeSat team, any CubeSat team, if you're not close enough, you will not get a satisfying answer. So they will not tell you exactly what happened. But I think within Australia, we are a very, very small community. We should be sharing things. Also, I think we should be having a form of some sort so we can write our complaints. I still remember in the old days when we first started building CubeSat using, I just say the name GOMS-based parts. We had a WhatsApp group to complain how bad their hardware is. I mean, they're not really bad. I think they're the best satellite provider at the moment. Well, at least one of the best satellite provider at the moment. But having a place to complain about things, knowing there are some common issues, it's not you, but the hardware itself that has the issue, that feels good, and that's a very, very much a healthy thing to do. So yes, to kind of get a quick summary, I think our center is trying to kind of open source and make things public as much as possible. We're certainly sharing things with our close partners. This is mainly because we're having IP issues and NDA stuff, regulations imposed by university, but we're willing to share more. I think a lot of things should be, they are generic enough. We should be able to share more things, and I really wish we can have a community and other people will come in and contribute more. We're trying to contribute to KUBOS as well on the open source platform. We're contributed one subsystem, the GOMS-based EPS system. We're trying to do more. We're quite slow, but we're doing what we can to build the community. So, and we do need a bit of a government support. I think, as I mentioned before, we're facing this 36,000K license fee. This is obviously as a barrier entry, and this is, I assume this is imposed by the government to, for the bigger companies, like telco companies and such. We also want a dedicated frequency for research, a cheaper commercial band fee from the government as well. So I'm showing this very last paragraph. Basically, if you look closer, basically all the countries, all the regions listed, they are big countries. They are big traditional, conventional space countries. Europe, US, even Russia, Japan, and China, India. But if you look closer, there are smaller countries, smaller regions like Africa or South America. These countries basically use CubeSat as a driven factor for this local space industry, and they did so well. There are a lot of things happening in South Africa. We're dealing with a South Africa satellite provider. They're really, really good. So I think this could be, for whatever government audience down there, you can consider, well, this could be the path that Australia can go. We are a relatively small country in terms of space resource, and population as well. So I think building CubeSat, start things from small, and doing good things, Earth observation, science, bushfire monitoring, it will be good for the country. That's my talk. Thank you.
Right. Thanks, Shuliang. So I encourage everyone to, again, go ahead to Slido. If you don't have a question, please do some upvotes to see which question is most relevant to you. I have a comment from Ben Hartig that says, I think an Australian advice on meeting international standards would be better. Do any of you have any thoughts on this? So something that's standards that apply specifically to the Australian context, given that we don't have a lot of support that, for example, NASA and ESA has. Maybe Andreas, do you think that's something that's doable, that's relevant to what we have?
Yeah, I was just about to put up my hand to answer that question. I think that as part of the creation of our own internal standards, it would be unwise to not try and match to other international standards as well. So, I mean, if we're dealing with CubeSats specifically, the CubeSat standard is an international standard. So we start with that and we go on. But I think there's going to be an inherent, I think, siding with trying to stick as much with international standards first, seeing what has worked, and then building up from that. But also in addition to that, we may be in a very unique position as a country, especially given that we all as companies are working together pretty good, to even make suggestions to the international community.
Right. Yeah. So I think there is a need for that, but how to get there is a bigger question that we kind of have to work together on. The other question that we have is, what kinds of missions would be in the national interest of Australia that can't be addressed by existing commercial or non-Aussie government satellites? Are there something that we can specifically propose to our developers and our Australian universities that can make us come together, that's unique to Australia? Maybe Sean, have you heard of anything similar? Do you have any ideas on that kind of missions, ride sharing maybe?
No, to be honest, nothing really springs to mind, because they're all the perennial favorites like fire monitoring and water monitoring, and that have been around since the year dot, that we still keep talking about and have various degrees of developed plans for. So those are the obvious candidates, but I suppose I'm not sure what to say if in 2020 we're still talking about those same missions that haven't really progressed anywhere with them. Maybe there is something a bit unique or different that someone else might hit upon.
Yep, Andreas?
Yeah, I can add to that. So I think, Sean, you're on the right track when you say the fire and water monitoring, but I think from the uniqueness that's not currently being offered, you're looking at new sensor technologies that are being used for those same things. So you might have a higher multi or hyperspectral imager that might actually be able to provide a completely different context for the same problem. So that's something that we could do independently that nobody else has done. In addition to that, some new radar technologies as well would put us in a unique position for a mission. I can think off the top of my head. I'd say in addition to that, some stuff that's still also really new that we should be looking at is anything relating to software-defined radio and additional uses of space-based GPS technologies, because again, they're unique and extraordinarily useful payloads for a number of different things.
Maybe this is a question for Marshall. Marshall, are you there?
Yes.
Yeah, you're there. Good. What can we do to reduce the barrier of reuse of software and testing between CubeSat teams? Do you think that what KUBOS is doing right now facilitates that and try to promote that? And what does KUBOS maybe can offer to solve this reliability problem with CubeSat? We know 50% of first CubeSat builders, they fail, and a lot of them are software comms problems.
Yeah, one of the biggest problems that I still see in the industry that existed when I first got into it is that right now, even for well-funded commercial missions, people are skimping on the number of engineering models they buy because they like don't want to spend the money. And guess what that means? Like that means fewer engineers have hardware and therefore fewer tests get run. And so I think one thing that we tried to do early on in KUBOS that I don't think was commercially viable yet, but I think would be a really great like university or like government mission would be to grab all of the commercially viable vendor hardware that is out there that is in any way like off the shelf available and just like throw it in a server rack somewhere so that people can like automate testing against that hardware. Every subsystem, every integration point, put them in a flat sat and throw them in the cloud. Like, again, I don't think it's a commercially viable business, although I'd love to be proven wrong. I just couldn't personally make it work. But I think that would be like a really low hanging fruit. Like you look at the mobile industry, for example. Like if I want to test an app that I wrote, you know, on for a phone, there are like a bajillion commercial services where they have banks and banks of every potential hardware device and revision of hardware with revisions of software that I can test my app against. And I can just pay, you know, however many dollars per month to go do that on that huge bank of hardware. We should have something similar for the satellite world where we've got actual working flight models of vendor hardware that's testable against flight software. Similarly, there are things that we did in the early days at Spire for the RDSat program that I think could be better done on a more industry basis. So for example, one of the hardest things about understanding how to test an attitude control system is like just understanding what the actual effect you're having without a simulator is. So like if you require a simulator to know what you're doing, it's like really hard to reason about sometimes about how your system's actually going to behave. We had this intern who came in and did like a reverse attitude control system where they basically just engineered rotors to actually rotate the satellite in reverse instead of using a simulation system. That was actually really helpful because we could actually simulate how like the physical camera system and what it did at certain angles, things along those lines, and like how it attenuated the radio signal, for example. So like those are the kind of things I think we should be doing outside of just like pure software, like thinking a little bit more like, just like, you know, there is no magic, like break it down.
Yeah, that sounds like a very good idea, but I guess the problem is a business model of it, isn't it? It's how do you then incentivize the business that provides that facility?
Well, as I said, I'm not sure that there is a business for it, but maybe this could be like a really good idea for a resource provided by maybe Andrew's group or someone like that that would have a more sort of, you know, like a common sort of system that maybe didn't need to be commercially viable, but maybe it just needs to like be sustainable and pay for itself.
Yeah. Okay, so again, I'd like to encourage everyone to maybe try to go onto Slido and do some upvotes. We'll probably pick 2 more questions before we end. So Eva has a question, Eva Cans. How important do you think natural causes of failure like space weather are for satellites, especially given that most companies don't want to report failures? So I guess he's implying that there are more failures due to space weather that actually are measured. So what can we do about it? Or is that true or not? Are we even debating, is that true? Maybe Sean, do you have some experience on that?
Yeah.
Yeah.
So yeah, I mean, definitely radiation events, effects from radiation are a well-known contributor to effects. But in my experience, even though you suspect it as the cause, it's often quite difficult to tie it down to a specific event. You can spend quite a lot of time tracing through recorded recent radiation activity and so on, and still be convinced that that was the reason, but it's often quite hard to show it. But nonetheless, yeah, I mean, definitely we all know radiation leads to, you know, a variety of different things, either recoverable or non-recoverable. So yeah.
So for example, when you did the mission at Canberra Space, Was radiation a big concern? Did you test vigorously against it?
I can't talk on behalf of them, but yeah,
Okay.
I mean, it's increasingly, people are paying increasing attention to it.
Oh, yep, Andreas has something to say.
Yeah.
Yeah, I can add to that. The answer is absolutely, I mean, yes. It's a huge contributor. Sean, you've covered it pretty extensively. But what I wanted to add is that it's not an impossible problem to track, and I think we are getting better over the last few years. At the very least, there has been some big leaps and bounds, especially on autonomous diagnostics. Even Saber's done some really deep work into that. To allow to do event matching and try and do cause effect analysis from within spacecraft. But the thing is like Sean, like you said, there's so many different factors that it could be space weather, or it could be space weather that causes something that then has a weird effect on something else that you really can't account for. But I think we'll get better in the next few years, like collectively, especially if there is that open sharing, especially of bus design or processor design. There's some people that are doing efforts to have FPGA-based event detection and correction. Sharing that sort of stuff is going to be super critical for us being able to get away from the common faults that happen from space radiation.
Thank you. So Tim Parsons has a question that is very futuristic. So what do you think is the ideal future state here? Is there any sensor that maybe we can end up with any sensor that can fly on a standard bus, or a nanosat that can fly on any launcher? Like, should we standardize, the bus, or that payloads can plug into? Should we standardize the way the sat interfaces with the launcher? Sean, maybe. Or I can hand it over to Andreas or Marshall if there's any takers. I think anyone can take this one.
Yeah, I mean, there are definite advantages for that, especially in replenishing large constellations or military systems, but also at the same time, these things are market driven. There may be reasons why certain vendors don't want that, so you can certainly create an environment where this is advantageous and the majority of people head in that direction, but I think you'll always find some obscure resistance too.
Yeah, Xuelang, do you think that it's viable that we end up with a standard bus? Engineering-wise,
I very much intended to say no, but I mean we can try to have a commonly accepted standard, a commonly accepted thing, which means you do need to kind of compromise things. When you build your payload, you can't really do whatever you like. You still need to follow certain things. What are the things commonly accepted? To that end, it's actually quite simple. As long as people are, like QB50, as long as people can reach some kind of common understanding, it doesn't have to be a standard. It can be 20 standard out there, but as long as we're going for one, that's fine.
Okay, I think with that question, that will be the last question that we can answer, where we've hit the 1.5 hours mark. I'd like to thank all the panelists here. It's been great having every one of you. Marshall especially, it's about your bedtime right now. And Andrew Barton sends his apologies. He had a meeting that he had to leave early. I did give him a 1 hour warning. We went over time by half an hour. So also thank you to everyone who've joined us. We've at some point hit mark of about 89. Thanks, Marshall. 89 participants. So it's not too bad attendance-wise. We do have a limit of about 90 92 participants in attendees wise. So I think this has been great for everyone. And before we leave, I just want to tell our panelists that we have a debriefing session. So the link is posted in the chats. I'll send the link again. You should check your email as well if you can't find it in the chat. So we'll do a debrief after this. But otherwise, everyone, thanks for questions. We will see that, try to answer some of them via email. You can email us x@exa, or you can find me at my my profile at exa.unsw.edu.au. Contact us if there's more questions that you really want answered. Thank you everyone for joining. Before I end, one last thing. Yes, we do have an Artemis Accord webinar. The Artemis Accord webinar will talk about how Australia will be affected by the Artemis Accords, as Australia is a Moon Agreement signatory and also being committed to its Moon to Mars program. So it's a very interesting legal / ethical conversation. It will be held on July 9th, 2020. Again, exa.unsw.edu.au. You should be able to find the link to the event there. Okay, with that, I'd like to wrap it up. Thank you, everyone. We officially end the webinar here.